slow. And if you know about this loop, then you know that doing a timing attack, you'll have to drop the line low early and then gamble it when the entrance of that loop would occur and begin shifting your bits out at that moment. I was lucky in attacking this in that you can slow down the serial traffic. You can make it speak as slowly as you please. You can even slow down the clock on some versions, which is handy. And then when you disassemble the code, you're dealing with a very different environment from a PC. On a PC, you have 4 gigabytes of address space, and that's in 32-bit mode. You have a kernel to deal with, and you have other processes that are playing along. If you're trying to hide code on a PC, there are all sorts of nooks and crannies that you can do it in. You can use the memory manager to actually change the view of RAM to a particular process. You have a hypervisor, and you can infect the hypervisor, and you can all of that crazy stuff. But none of that works on an embedded system. And none of this works on an MSP430 or an AVR because you've got a small address space and a single process. You have no kernel. You don't even have a runtime linker. You have no dynamic symbols of any kind. In many applications, you won't even find function pointers. But at the same time, there's no I2Pro support. You have to write your own tools to do these things when you're the first person analyzing code on a given chip. So I wrote a quick tool called MSP430 Static that I really wish someone would replace. It's written in Perl calling SQLite, which calls back to Perl, which would be suicide if you were trying to do it for a PC program. But the longest word that physics will allow on this, the longest program that physics will allow on this chip is 32,000 words. A 32,000 row table is not that difficult to query. So you can write a query. You can select the hexadecimal address of a function along with its name, ordering it by the addresses in descending order, and you can limit that to 5 results. This will give you the 5 functions that are in the highest regions of memory. And this is useful if you have an application that's mixed in with a bootloader, because the bootloader will be above a given address. You can draw memory maps very easily just by selecting code out and piping the rows through something that translates it into drawing instructions for a graphics program. Here you can see a very small program that begins around 4,000 hex. The application data is in red. The executable code is in red. And it's easy to recognize executable code because it disassembles cleanly. Even though there are 16-bit instructions, not all values for a given instruction mean something. So wherever a given instruction is valid, you draw that in red, and wherever it's invalid, you draw it in gray. You'll wind up with solid red for executable code and mixed red and gray for unexecutable code. And this allows you to distinguish between the two. You can also count upon the compiler placing them in particular regions. So in the case of GCC, executable code comes first in flash memory, followed by data. You'll also note that with many compilers, the data will immediately be copied to RAM as a bug. So if you find the same content in both RAM and ROM, you can be reasonably certain that it's data and not code. This is a more complicated image, one taken out of a physical device. This is a JTAG debugger that Texas Instruments sells for debugging their chips. You can see here in red is the main application code. Up here you have data tables, which are loaded in for identifying target chips. And then at the very top, this red code here is actually a bootloader that proxies interrupts to lower code. And because it proxies interrupts, the password will be the same on all versions. And you can actually separate these two applications. To separate individual functions, you can bank upon there being only a call to an immediate value. So wherever you see a call or a branch, you know that the address that comes after it, which is often a distinct word and very easy to search for even in binary code, you can bank that word refers to the entry point of another function. And you can find its exit point because the exit point will be after the last relative jump. So if I have a JZ or a JNZ or another jumping instruction after a comparison, in say an if statement or a while loop, or if I have a switch, there will always be a default clause which jumps to the end of that. So I look at all of these different relative jumps, and the return function will always be after that. Once you know where functions begin and end, you can figure out which ones call each other. So you can search through a function, you can say, give me all of the targets of call instructions. And then you can generate a call graph from this, where every function is a vertex, and then every function call is an edge in graph theory. And there are great tools in Unix for rendering these. So here you can see a reasonably large application. All of the unused interrupts come as this sort of long jump here. And you can find particular functions very easily because I/O is mapped to a particular address. Your output buffer for the first serial port will always be at the same address. So if U0's transmit buffer is at 77 hex, and you see an instruction that says move the byte in R11 to 77 hex, you know that that instruction is writing an output byte. If you know what's plugged into that port, which you can easily find by looking at the board and tracing the wires, then you can tell that this, say, transmits a byte to the PC, or this transmits a byte to the radio. And then you can give it a name. And you can search for the list of your names very easily through SQL or whatever you might write your own tool in. Then you can dump out a hash of that, and you can compare future programs to it. If you have access to example libraries, you can build up databases of the hashes for all of the standard functions. And then you can identify them later. And the MD5 checksum of the code is not a creative work. It's not copyrightable in the same way that the code might be. So even though I can't give you a copy of the code that I've identified, I can give you a copy of a one-way hash of that code along with a name that I've given it. And I can include this list with my tool. So when you're running the tool, you type 2 commands, and it will recover the name of every function in your application that I've seen in any of the functions that I've ever taken apart. You can also look by call frequency. There's an operating system for this called TinyOS. And it does a lot of mutual exclusion calls. So if you look at a graph, it'll be this rat's nest where 2 functions get called 1,000,000 times. And those 2 functions are atomic start and atomic end, always. If you have a new large application that's complicated, not something small, and you search for it for the most popular functions, it'll probably be these 2 if it uses multi-threading. You can also look at the interrupt table, because in the same way that there is a standard word at which you write all of your outcoming bytes, there's a standard address at which the operating system looks, not the operating system, at which the hardware looks to figure out where to jump when an incoming byte arrives. And you can run through this list, and everything has a meaning by hardware, so you know that it will apply to your firmware image. The timers, for example, will usually jump to task handlers, and the I/O will usually jump to button handlers or things of that nature. It's very expensive to poll a switch to see when the button has been pushed, as far as power is concerned. So you don't do that. Instead, you put the chip to sleep, and you say, wake up and run this interrupt handler when the button gets pushed. But you can't specify which. That's done by hardware. And that makes it easy to reverse engineer. And then you can see here that these interrupt handlers are all unused. So if you see many different interrupts going to the same target, it's probably an unused handler. All it's doing is making sure that the chip doesn't crash